Hello, everyone. I want to talk about spontaneous or product-favored processes today. And this has to do with an extension of thermodynamics. And what we were talking about was delta H, calculating delta H or heat. Well, it turns out that most of these processes that produce heat, in other words, exothermic reactions, are product-favored processes, or what we call spontaneous. It turns out if we take a look at a reaction pathway, and we have the reactants and the products. So these are the reactants, these are the products. When we get over that little bit of energy called the activation energy, the process naturally goes on its own down to the products. Okay, whoops, those are products, excuse me. So when we do this, as it proceeds to the right, this is a natural thing. This is a spontaneous process. These are exothermic processes, or exothermic processes are typically spontaneous. In other words, they just go. For example, a non-spontaneous process would be boiling water. Again, it's a physical process. It's not chemical, but again, that's always an uphill process. If I'm trying to get to boiling water, I have to go uphill. I have to keep supplying heat. So boiling water at room temperature is non-spontaneous according to the conditions that the water is in. So there's a bunch of slides I want to go through. And again, feel free to pause at any time to write down what you see. These are all New Jersey Center for Teaching and Learning, so it is a little bit wordy. So again, you got to kind of take what you have here. So reaction is said to be spontaneous if it just goes without outside intervention. Again, you have to start. Now, the spontaneous doesn't mean fast. Okay, spontaneous just means automatic. Okay, and again, kinetically slow. We'll talk about kinetics as we come to chapter 12, not until the new semester. Okay. So this reaction, as you can see here, favors the formation of products because they're more stable. In other words, they have lower energy. So if we take a look at this reaction right here, notice the reactants are higher than the products, just like I just talked about. Okay, so the problem is it's a very it's a very slow process because it has a humongous activation energy or barrier it has to get over. Okay, so a better word for spontaneous, they say, is product favored. In other words, you're going to get a ton of product. Okay, product favored means that products predominate over reactants in the reaction. In other words, there's more products than reactants when the reaction is done. Okay, period. So an example of this is something that is thermodynamically favorable, where heat flow goes from hot to cold. That's spontaneous. Heat, pressure always goes from hot or high to low. Okay, so that's a great, and again, that's more of a physical thing. But again, you can see that anything where we have emission of energy, or exothermic, I shouldn't say anything, but most things are typically product favored. Reactant favored processes are non-spontaneous. Now the reactants have a lower energy than the products. That's an uphill process. So these are thermodynamically unfavorable. Okay, in other words, it's not going to really work. So an example of this, again, it's not a reaction, it's a physical thing, is where heat flows from a cold object to hot objects. Things don't naturally just heat up in the room. Okay, they tend to have heat applied to them. Okay, this reaction is spontaneous. When I take potassium and put it in water, I automatically get these two products. Once it hits that water, it is automatic. Okay, so the reaction energy, this is a quick reaction, so I have a very small activation energy, and it just goes. Okay, so this is a good example of a chemical process that is spontaneous or product favored. Okay, rusting is also spontaneous. Okay, so here's another example. This is where iron reacting with oxygen automatically gives you iron 3 oxide. Okay, so steel, when exposed to oxygen and water, it's a slow process, but eventually it does work. So when you take a look at the the Golden Gate Bridge here, they actually have to paint the bridge. One of the most effective ways of stopping corrosion is just preventing the oxygen from getting to the steel itself. So the whole thing is painted, and they hire people to do that. Okay, so again, a slow process, but it is spontaneous. Once you get a fire going, like such as your stove or a Bunsen burner, man, it just goes. That's a spontaneous or product favored reaction. Okay, now reactant favored is the exact opposite. We've already talked about this. These are three processes. So rusting, well, like we looked at, doesn't go back to this on its own. It requires some kind of input of energy to do that, like a tremendous input of energy. So we would call that a non-spontaneous process. And you notice something that is definitely not happening is where CO2 and H2O, this is again global climate change. It would be awesome if we had this for global climate change, where we get fuel out of that. Okay, that only happens over thousands and thousands of millions of years underground under tremendous pressure when you have the right conditions. So again, that is a non-spontaneous process or a reactant favored process. So what is continuous outside intervention? It's some flow of energy, so I haven't really defined that. So this could mean heat of a reaction, heating the reaction, or applying pressure, or working to get it done. For example, again, it's a physics example, but a ball rolling up a hill is not necessarily a spontaneous thing. You have to apply work to take that ball to the top of the hill. Okay, so again, you have some outside intervention. Now, a spark is not outside intervention. A spark provides the activation energy that's necessary to make the reaction go. So again, the outside intervention means a continuous supply. Spark is one and done, okay? So a spark is not outside intervention, a continuous outside intervention, I should say, okay? Processes that are favored with temperature, processes that are temperature dependent may or may not be product favored, okay? So again, if you take a look at this, it says processes that are favorable at one temperature may not be favorable at other temperatures. Take the process of melting ice. It's spontaneous at temperatures above 0 degrees Celsius, okay? But again, melting is non-spontaneous, or at least spontaneous in the opposite direction when it's below 0 degrees Celsius, okay? So just be careful on temperature dependence reactions, okay? Now, going a little bit further here, chemical reactions are processes that disperse energy. They tend to go hand in hand. So again, I haven't talked about this yet, but now we're going to talk about something called entropy. And when things tend to get more random, when things spread out, when randomness increases, we call that level of randomness entropy. Okay? Now, entropy is very difficult. There's no single definition for entropy, as it says. We're going to look at entropy as it talks about the dispersal of energy or dispersal of matter, okay? So a process that is product favored, this is huge right here, a process that is product favored is one in which the energy spreads out or disperses. In essence, there's more disorder. And entropy can be described, although I've heard this argued against this, entropy is the measure of disorder. It's rather the process that leads to disorder, okay? So we're looking for more disorder, and more disorder means higher entropy or greater entropy, okay? So as an example, let's turn to the heat transfer of a hot object. Again, a more physical thing, but it's okay. Let's take a look at this. We have a hot pan on the stove that cools to room temperature. The thermal energy is initially concentrated in the pan. Now again, if the first law of thermodynamics says that you can't just create or destroy energy, but you're just going to change form, this cooling causes the energy to be dispersed or spread out or more random. So the dispersal of energy is something that will naturally happen. That is a spontaneous process. Therefore, it is the entropy increases, and that is a thermodynamically favored thing. We want that. That is something that's going to happen automatically, okay? Thermodynamically favored means something that is going to happen. So take a look at this here. Dispersal of energy occurs because it is much less probable to have energy concentrated in a few particles and more probable to have them spread out over many particles. Take a simple situation in which we have 3 particles, A, B, and C, and 3 units of energy where the star is the unit of energy. Which of the following arrangements is more probable? Okay, so if we're going to spread out this energy, it's concentrated here, a little bit here, and here it's spread out. I think three is the correct answer. Okay, choice 3 is the correct answer. So we want to spread that energy out over particles. Okay, now I also mentioned that energy dispersal spreads out, but I also said that matter also wants to disperse. Matter wants to spread out. So in other words, the dispersal of energy, or the amount of entropy, or the delta S, because entropy is now going to have the designation of S, delta S increases in a huge way as we move to the left. There's a tremendous amount of entropy here, a tremendous amount of disorder. There's less disorder here, and actually much, much less disorder here, okay, because they're locked in bonds, okay? So when expansion of gas, is this expansion of gas thermodynamically favorable? Okay, now let's look at the probabilities. The probability, so when we take a look at this example right here, this is closed. All the gases are here, okay? When I open up that valve, the chances, the probability that these particles will spread from here to here is huge. Particles would rather go to more randomness, more dispersal. So the probability of taking them positions in A and B, the A and B sides, is much bigger than collecting in one spot. See, there is a chance that all these particles here and here will collect over here in this corner, okay, or just in B. But that's only one chance. There's so many, there's a plethora, there's almost an unlimited amount of chances that they will spread out between the two when the valve is opened, okay? So again, dispersal of matter, dispersal of energy is a spontaneous process because we increase entropy. Compressing a gas, is that thermodynamically favorable, okay? So will the bromine ever spontaneously move from flask A and B into just B? I just discussed that, so I got a little ahead of myself. So the example is it's not thermodynamically favorable because it's highly improbable. There's a low probability that they all go to one side. This is an example of a process that can only be reversed by doing work on the system to compress the gas back into B. Okay? All right. So, products favored versus reactant favored processes. Identify each of the following processes. So again, we'll go over this in class. You can take a look at this. I'll show you the answer. I think that's been really helpful. So again, there's a bunch of them. So there we go. And the answer is, again, pause it when you need to. So those are product favored versus reactant favored. Okay, PF versus RF. Okay, pause the video when you need to. Okay, so summary of product favored processes. Here it is. Check it out. I'm not going to go through this quite again, but check out what we have there. And again, there's a bunch of questions here. Again, pause where you need to. The correct answer to this one is B. Okay, the correct answer here is D. There we go. Oopsie. Okay, and we'll stop there. Okay, I will move on to this with this different video.